Hi, Guillermo. How are you?
Hi, teacher. Great, and you?
Great. Also, waiting for
What are
you
you doing
guys to
today?
get connected.
Hi,
Pretty well.
teacher.
Hi
What are you
there.
going
How
to
are
do
you?
today?
Fine, and you?
Nothing. It's dangerous today.
Yeah,
Many
it's
jobs.
dangerous, but with spending time with the family and see all the I see live transmission.
Well, we don't really care about it. And we are only three, my wife and my kid.
Yeah, that's kind of true. It's more like a way to skip responsibilities and have a great time. But right now in a pandemic, it's difficult.
Yes, it's fun when you are with the whole family, no?
Yes, exactly.
But just three of us, I don't think we're going to be doing much of that. Maybe we just sit and play some Xbox.
That sounds nice. It actually does.
Okay, let me open the call roll. Here it is today. So tomorrow you don't have classes. That's great for you guys. Okay, so we got skills, Guillermo skills. Daniela Olavarria, Gerardo Avila.
Hello, teacher.
Hi there. We got Maria Inés and Dani Rueda. García Uriostegui. Okay. Rodrigo, Daniela Silva. Eloy Ramírez. Silva. Daniela Galán, Monse Rodríguez. Ale. We're missing María del Pilar Uribe and Rodrigo Verástegui. Daniela Galán, were you able to watch the video from the last class?
Yes, teacher.
Okay, so did you accomplish the homework?
Yes.
Okay, I'm glad.
Thank you, teacher.
You're welcome. Okay, let's start. Already give 5 minutes. Today we're going to have a long theory class. Sorry for that, but it's part of the, excuse me. It's part of the course. Okay, nobody's going to be bothering anymore. So let's share. I need you to pay attention. It's a little bit confusing, but we can do it, okay? Monse, she just connected right now. No. Okay. There we are.
Hi, teacher. Sorry.
Hi, Maria Pilar. Remember me to take your let's do it right now.
Okay, thank you.
There you are. Okay. Somebody else, Rodrigo Verástegui. Not yet? Okay. So let's start. Today we're gonna see some theory. We got to understand how the simplex method works. We have been able to use it through the solver, but we need to understand somehow how it works, and we're gonna continue with the exercise of the window or glass company, okay? So first, I'm gonna explain it from the geometric point of view, and then we're gonna set the algebraic point of view. And next class, we're gonna be doing the algebraic point of view, okay? It's a lot of math. I hope you don't get lost. If you need to stop me, let me know, okay? So first, we're gonna start with some terminology that somehow we already know it, okay? Do you have a black box in front of the presentation? No?
No, teacher.
Okay. Okay, I'm glad to hear that. Okay, Daniela and Monse, is there some reason for putting your screens on?
Yes, because of my internet, teacher.
Yes, me too.
Okay, we're having internet problems. Okay, so let's pay attention to this. We're gonna see how in a, let's say, remember we did the geometric solution for the glass for the window glass company, that we were like drawing the lines until we came all the way to this solution. Well, now we got to understand how the simplex method comes to that solution, okay? I'm gonna try to explain from a point of view of also a graphic point of view. They call it the geometric point of view, okay? So we're gonna work first from the geometric point of view and then the algebraic point of view, okay? In order to understand one, we got to understand, in order to understand the algebraic, we better understand the geometric, okay? Now, terminology. Constraint boundaries are all the line that marks boundary of allowing the corresponding restriction. So this is one boundary. This would be another boundary. We got 1, 2, 3, 5 boundaries in our problem, okay? Now, the points of intersection of the boundaries, for example, these points, they're called the corner point solutions, the CPF solutions, corner point solutions. F goes for feasible. Okay, we're gonna check that later. So we got 5 feasible corners here. We got 1, we got 2, 3, 4, and 5. But we also have 3 non-feasible solutions. This one, I'm gonna put them in a square. They're non-feasible solutions, okay? Because they don't belong to the feasible region, okay? And whenever we talk about CPF, we're talking about this one, this one, this one, all the ones that are in the feasible solution area, okay? Now, each corner point solution lies at the intersections of 2 constraint boundaries. In order to have a corner, we need 1 and 2 boundaries. Otherwise, there wouldn't be any corner, okay? So far, okay? Now, when we have 2, we're gonna have 2 solutions. Yes?
Can you go back just for a second so I can take a picture?
Yes, I'm gonna load
Thank
this.
you.
Don't worry, I'm gonna load it, okay?
Okay,
But
thank you.
yes, go on and take the picture, no problem. Okay, now, 2 CPF solutions. Remember what was CPF solution stands for, Gerardo Avila? Remember? It was corner point feasible solutions, okay? They refer to these corners. This is one CPF, this is another CPF, so it says 2 CPF solutions are adjacent So we got here one CPF solution, and we got here another CPF solutions. So they are adjacent to each other if they share constraint boundaries. So this one is adjacent to these ones because they're sharing this boundary. Do you agree? 0, 6 is not adjacent to this one because they're not sharing the boundary, okay? So that's a condition. Now, the two adjacent CPF solutions are connected by a line segment called edge, okay? So let me go back. This is what we call the boundary, okay? But from this point to this point, between both CPFs, this is gonna be called edge. Is what we call in Spanish arista, okay? So this is an edge, okay? That lies on the same shared constraint boundaries, okay? So each CPF solution has two adjacent CPF solutions. Let me go back. So if we got this solution, if we got this CPF solution, well, it will have 1 and 2 adjacent solution, okay? And this CPF solution also has 1 and 2 CPF solutions. Each CPF solution has at least 2 adjacent solutions, okay? And then we're gonna say a definition. Optimality test is if a CPF solution has no better adjacent CPF solution, and this is gonna be measured by the Z. Remember how did we measure Z? 3x1, 3 times x1 plus 5x2. So if there's no better solution, then that CPF is gonna be our optimal solution. Let me go in advance. Let's say we start always in our 0, 0 point in the region. And then what the geometric solution makes says, do we have a better adjacent solution? Yes, we do. Okay, so let's move to the next adjacent CPF solutions. And then they question again, do we have a better adjacent solutions? Well, we got 2, this one and this one. And this one is better because Z will be increasing, okay? So we move to the next one, okay? Now we are in this one. Do we have a better solution? No, we do not have a better solution. So this point will be what we call the optimality test, okay? They're questioning between. Each time they're questioning, okay? So if I'm here, I question, is this solution better than this one and then this one? No. Okay, let's move to the next one that increase, okay? And that's how it moves. It starts in 00 and starts moving all around the different CPFs, all around the corners, okay? So it follows some steps. We're gonna see the steps, okay? Now, if a CPF solution has no adjacent CPF, better adjacent solution, okay, then that means we're in the optimal solution. I already say that before, okay? So it says, for example, the corner 2.6, the CPF 2.6, this one, must be optimal simply because here C is 36, while the adjacents are 30 and 27. So this one has to be my optimal. It's always, when we're in a corner, the simplex method, it's always comparing against the other 2 adjacent corners, okay? Now, this optimality test is the one used by the simplex method for determining when an optimal solution has been reached. By that comparison against the other adjacent CPF, that's how we reach to our optimal test, to our optimal solutions, okay? So, and here I already have done my conceptual map. I'm gonna load it for you, okay? Now, let me continue. Let's say, we talk about terminology, the definition for constraint boundaries, the definition for CPF, corner point solutions are formed by two, feasible, okay, and non-feasible. So all my corner solutions, point solutions, are the adding of two. Here we say we had 5. Here we say we got 3. So we got 8 point solutions. Okay. Terminology, we talk about those adjacent CPF solutions. They share boundaries, and those boundaries in the feasible region are called edge. Okay. We also talk a little bit about optimality test. If a CPF, if a corner has no better adjacent corner measured by the Z, then that's the optimal solution. Okay, that's a criteria we're going to be using right now. Okay, so we're going to start like following some steps. This is a small one. Okay, and then we got iteration number 1, and then we go to iteration number 2. Now, in order to make it easier, I did this kind of comparison table. Okay, I think it will be easier for you guys to follow me here. So we start with the initialization. Okay, let me move a little bit this green box. Okay, so we start here. This is our starting point, initialization. Oops, it moved my box. Okay, initialization, okay? So we move to a better adjacent CPF solution. So here at the beginning, my start point, most of the times is gonna be the origin. That means the point O, comma O, okay? Now, we're gonna jump. This is my initialization. I'm gonna go straight forward to my optimality test, okay? Before I take a decision and go to the other steps, I first take a decision. And it says, for C, X1 and X2, that means values 0 and 0, can we conclude that the adjacent CPF solutions are better or worse? Okay, so we go to our adjacent CPFs. If we go to the graph, where's my mouse? Here's my graph, here. So we start here, okay? And we go directly to the optimality test. So what I'm saying, is this number better? This C0 is better or is worse than C equal 30 or Z equal 12? Well, it's not good, but we got a better one for the point, and we're just talking about adjacents, okay? We're comparing among adjacents with this edge and this edge also. So for C06, we got 30, and this is better, but for this one, it's better, but we got a better one that it's 06, okay? So we're gonna go to our next CPF. So what we're gonna be doing is we're gonna be moving from this point all the way to this point, okay? Now, so it says we move to a better adjacent CPF solutions. We have done that, and we start our iteration number 1, okay? This was just the initialization. Now, between 06 and 40, we choose 06 for Z because we get a better value, okay? We choose the edge that enhances Z, okay? So O6 is the one that enhances C, okay? Our second step will, so if we decide to go this way, we'll go up, 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 and we stop here. This point is when we have our boundary. Remember when we say this boundary is 2x equal 12. We cannot go over this boundary, but because then we'll be outside our feasible region, okay? So we stop here, and then we solve for the intersection of the new boundaries. Now my new boundaries, my corner, my CPF is gonna be 0.6, and I got 30, okay? So we go to the optimality test. Do we have adjacent CPF solutions better than 30? Well, yes, we got one, and the other one, no, it's worst, okay? So we're gonna choose the next adjacent CPF. That means we're gonna be moving now to this one. So we move to a better adjacent CPF solution, okay? Now, between these two, 2,6 and 0, we choose 2,6 because it's the one that enhances Z, okay? We're always looking to increase C, okay? Now, we stop when we get into this CPF, and here we got this equation, okay? The equation is 3x1 plus 2x2 equal 12, okay? So we solve the intersection of the new boundaries. The intersection is gonna be at 2.6, and here Z is gonna be 36, okay? And we go back again to the optimality test, okay? So we got here a question mark. Does C at CPF at corner at CPF 2.6 equal 36? Do we have a better adjacent CPF solution? No, we don't. The next one is 27 and the next one is 30. So we stop here because we consider this to be our optimal solution. I went a little bit fast. Do you have questions? I went quite fast. I can repeat everything if you want me to repeat.
Teacher, I didn't understand where those
From the beginning.
the 2x2 es igual a 12, 12.
Okay, 2x2 equal 12? Okay, that comes from our original problem. Let me close here this. Okay. So this 2x2 comes from our original problem, okay? It was one of the restrictions, and then we come to the conclusion here that x2 would be equal 12 divided by 6 equal 2. So we have that one of our boundaries would be x2, no, sorry, this is 6, no? x2, no, it's,
2, teacher.
divided by 2 equals 6.
Okay.
And then we say that one of our boundaries was x2 equals 6. Let me find it. Give me 1 minute. So you can remember. I got it someplace over here.
No es porque quiero perder, pero sí quiero.
Okay, here we got the equations. These were our original equations, remember? So we got, we say that our boundaries, our restrictions were x1 less than 4, 2x2 less than 12, and 3x1 plus 2x2 less than 18. And then we have our non-negativity restrictions. All of these are boundaries, okay? So going back to our image here, I cannot erase that part. So if we remember, this boundary was given by x1 less or equal to 0. This boundary was given by x2 less or equal to 6. Okay, but on the first steps, we saw that this number came from 2x2 equal or less to 12. Okay, but we simplify it. And this boundary, the one we have like this, comes from this formula. Now, this boundary is my non-negativity for x1, and this one is my non-negativity for x2. Do you remember that part or no?
Yes.
That's where it comes from, Gerardo. Okay?
Okay. Thank you.
Okay, we're working on the example, remember, okay, in order to understand this. So the main idea of this graphic option, it's mainly like saying what really simplex method does is starts at this point, makes a comparison between this one and this one that are the adjacent CPF solutions, okay? And then depending, it takes decisions. Should I go this way or this way, okay? So it takes a decision to go this one, okay? And this one says, no. Now, I won't want to give you more information because you're gonna start to get a little bit confused on that, okay? Just, it works this way, okay? Now, if this solution in another problem comes to be better, it could go to this direction, okay? But this is somehow to make it easier to understand how it works. So it goes to this one and then makes again the same question. Which one is better, this one or this one? Well, this one, okay? So we go to the next one and then makes again the same optimality test. Which one is the best? Let me move this black. Which one is the best? This one, this way, or this way? Well, none. So, okay, so then we stay here. Okay, that's what we're doing from geometrical. And when we say geometric, it means graphical point of view. Okay, is it clear? Okay, so this was important for you to understand it because we're gonna go over the algebraic solution, okay? And the algebraic solution requires more issues, okay? Let me go over here. Here, put it here. Okay, so what we just saw, we had an initialization step, okay? And in this initialization step, we always gonna be choosing as a start point, okay, the origin, always, okay? That's what the simplex method does, okay? And then we just go directly to the optimality test. How would you explain in your own words this optimality test? Dani Reda, any idea?
It's when you like ask yourself which point is better or maximizes C.
Okay, nice. We're in a CPF standing in a corner, and then we ask to our adjacent corners, are they better or they are worse? And if they're better, we move to one of both, okay? That's what the optimality test makes exactly. Thank you. Question, if there's no better, then we stay with this one, okay? Okay, so after the initialization, we start with iteration number 1. So we move to a better adjacent solution. And what we're gonna be, we choose the best edge, okay? We stop at the new restriction. And if we go on the graph, watch what we did, we choose the best edge here. So my best edge is this one. So we stop in this restriction, okay, in the restriction, okay. And then it says, we calculate the new Z value and we go again back to the optimality test, okay. So that's how it works. And then it says again, I am in a CPF solution and I do a question. Do we have a better CPF? Adjacent CPF, that's a condition. It has to be adjacent, okay? Yes, we do. Okay, then move to that CPF and we continue and then we go to our second iteration, okay? And then we just repeat the steps. We choose the best edge. We stop at the new restriction. We calculate the new Z and we do again the CPF. Okay, we're in a CPF. We make the question and we compare to the adjacent CPFs. Are they better? No, they aren't. Okay, we stay here and this is my optimal solution. Did you get the whole idea? It's not really that difficult, no?
Yes, teacher.
A little bit confusing, but not really that, not to get that lost, okay? Now, there are 5, yes, there are 5 or 6 solution concepts that have to be accomplished, okay? In order to these iterations happen, okay? So the first concept, the first solution concept is the Simplex method focuses only on CPF solutions. That means it only works on corners, okay? It will not take a solution from here, or here in the middle of the edge, never. They always work with corners, okay? So it always works with CPF solutions, no more, okay? That's my first solution concept. Second, Daniela, what are you doing? You're taking notes? Really? Okay, even though I'm gonna load it, okay? Okay, second, my second solution concept says the Simplex method is an iterative algorithm, okay? So it goes and over iteration, and iteration. Here we started here, and then we have our first iteration, our second iteration, so, and it repeats the same steps, okay? So it systematically repeats the steps, okay? So it works with an iterative algorithm, okay? Now, our concept solution number 3, it says, initialization of the Simplex method chooses the region, okay? We're gonna start always here in the region, okay? So that's another key solution, okay? Can I continue?
Yes, teacher.
Okay.
I have a question.
Yes.
So you start there in the region.
Yes.
Can
yes.
can you go to the right or always to the left or to the best way?
It depends. You start here and it will immediately make the optimality test. If you're here, it says, okay, here, my CPF, okay, solution, here for the 0.0, 0, it's gonna be 0. Okay, so my optimality test says, do we have a better adjacent CPF? Yes, we do. How do we know that? Okay, well, here, because we're in a geometrical solution, we can see that this one is 12 and this one is 30, okay? That's why.
Okay. And if they were like 30, like the opposite,
then it will go on this way, okay?
to the right. Oh, okay.
Yes, yes, it will always go to the one that enhances Z, okay? That one that increases more Z, it will go to that side, okay?
Okay, thank you.
So solution concept number 4. Giving a solution, a CPF, after we have given a solution, a CPF solution, okay, it is much quicker computationally talking to gather information about the adjacent solutions than about other CPF solutions. So for the computer, it's easier to know more information about these corners than about all the possible solutions here. I mean, they're infinity, do you agree? So it will never finish. Instead of that, they just go over the CPF, over the corners, and it's easier to work with 2 CPFs than with a huge amount of feasible regions, okay? So instead of going like this, like steps, going all the way up directly, that will take a little bit more time. We go over the corners. Maria del Pilar, you're gonna fall asleep in your couch. Okay, tomorrow you're not working, so this is your last class, no? No? Okay, too bad for that. Then you should take a coffee. Okay, solution concept. Another key solution. Simplex method examines each of the edge of the feasible region, okay? So it works with only with the edge. It doesn't matter what happens in the middle of this region, it will be working always with the edge. It doesn't takes in account the rest of the area, okay? And that way, we reduce the problem to few corners, okay? And solution number, concept 6, the last one. When we have a positive rate of improvement of Z, it implies that the adjacent solution is better than the current CPF solution. Now, let me explain you that one. If we are in this point, okay, here, my formula for Z was 3x1 plus 5x2, okay? So I got to take a decision if I go up to this one or I go right, okay? Now, if I increase in 1 unit, which one is better, x1 or x2?
X2.
X2?
Yes, because here my coefficient is 5, while here my coefficient is 3, and 3 is less than 5. Do you agree? So,
Yes.
so that computer automatically decides to go to where it will increase more, to this for x2, okay? So it's gonna move forward x2, okay? Now, at this point, let's say we make the same decision and then we say, okay, for Z equals 3x1 plus 5x2, we increase 1 unit. And you will say, well, let's go to x2. Yes, but remember, you're already in your boundary that it's a restriction limit. So you only have 2 options. Either you go down or you go left. So if you go down, that means it will decrease for what you got right now. Do you agree? At this point. But if we go right, then we'll increase. So we go to the right one. We're always gonna look forward for an improvement of Z. That's my solution concept number 6. We're gonna be always moving to the solution that improves the value of C, okay?
Teacher, I have
Question?
a question.
Yes.
Yeah. I don't know if I'm correct, but please let me know. So if we have this graphic method, for example,
Yes.
if we identify oh sorry, how does it say the CPF?
Yes.
That it's at the top and at the right point, for example,
Yes.
in this case 2,6.
Mm-hmm.
It, I don't know if we can identify for sure that if we identify that corner is the optimal solution for almost all of the cases.
Yes,
Is,
for this situation.
okay.
Yes.
Okay.
What's your question?
Can I say in Spanish? Because I already tried to do it in English, but I don't know if you understood.
Yes. Go on.
O sea, profe, sí, en diferentes casos podemos identificar que está el punto hasta arriba y a la derecha. O sea, gráficamente podríamos decir, sin calcular que obviamente está mal, decir que esa es la mejor opción, la como más óptima.
Yes.
Okay.
Yes, and that's what we did when we did it graphically, the first solution. Remember, we start moving our equation until we hit this point, and this was our best Z value.
Yeah, but only for the maximization cases, right?
Yes. Now, in this, what we're doing right now is that, let's say, okay, we understand how to do it graphically. It was quite easy. The problem here is, what if we want to do it through a computer, like a robot, okay?
Yeah.
We want a computer to come to a solution, and if we're able to make it through a computer, that means then that we can introduce more than 2 variables. We can introduce the number we want of variables, okay? So if the problem is of 15 variables, the computer can work it, okay? We're not going to be able to do it. We're not going to be able to do it either graphically or either algebraic, because it will become a very, very complicated solution.
Okay.
So now what we're looking is how can we make this in a more automatic manner, okay? So we are trying to understand. My point of view is what we're doing, or my thinking when I explain this is, I think that, let me go to the first one. This George Dancing, he received a Nobel Prize for this solution, okay? He developed this Simplex method, part of it, okay? The beginning of the Simplex method. And my thinking is that he, in 1947, he must be thinking this, what we're talking right now. What can we do in order to make this a more automatic solution? Let's say, what if we work with corners only? What if we move like this? Can we ask the computer on a mathematical basis do that? Yes, we can. Well, if we can do it, then we can work with lots of decision variables, almost everything, okay? And he received a Nobel Prize for this, okay?
Okay, teacher, thank you.
Okay, so he started with these observations, and then he come all the way to this iterations, and for sure he say then, well, my key solution concepts are this. We start at the origin. We're going to be only working with corners. It's going to be iterative. It's going to be repeating each time. The steps are going to be exactly the same each time, nothing new. Okay, and what else? It's going to be easier to just calculate corners than just going through all the feasible region. You got infinity solutions in the feasible region. Do you agree?
Yes.
How many points do we have in the feasible region? Infinity points. So there's no way we can work with it. okay? It will be more like an approximation solution. Yes, we can work it like that also, but it would take a little bit more, okay? Than just going through the corners, okay? And so he established these ideas in order to say, okay, now that's from the point of view of graphic, but now we got to understand what can we do more from a point of view of algebraic solution, okay? Do you have any questions so far? Something you want me to repeat, go back? Everything has been clear?
So far, so good, teacher.
So far, so good. Really, you understand faster than me, I can see. Okay, I'm glad to hear that. Okay.
No, but because you were a good teacher.
Ah, you're going for a nice grade. Okay, so now in order to make this visual solution work under a mathematical solution, and the straight words are, in order to bring this geometric procedure into an algebraic procedure, we got to make some changes in our original form of the model, okay? Our original form and the way we introduce the data in the solver was like this. We have a maximize an optimization equation, okay? And then we have our restrictions, remember? And then we just do the input data in the solver, and all the changeable cells change nice, and we come to a nice solutions. And we even were able to know the limits with the sensitivity analysis, okay? But how can we mathematically work this, okay? So those who study engineering, and it's not the case, we work with metrics. Do you know what's a matrix? No? Okay. A matrix, it's when we have something like this, like x1, 2, x1. Okay, let me go to an example. When you were in high school, you study the solution system. When you have three equations with three variables, that's what we call a solution system. Yes or no? Let me choose an example for you. Give me just 1 minute and I'll come to an example. Here, let's ask. Now you know where the name of Edge comes from for Microsoft, okay? So, sistema de tres ecuaciones con tres variables. And then they show you different ways to solve this, okay? Here we got an example. Something like this, okay? Let me print this, okay? And then I go back to our presentation. Don't you remember seeing that at high school?
Yes, teacher.
Of course you did. Okay.
More or less.
Okay, so remember, and of course you did, because then they show you when you have three equations like this, okay, where you have equation number 1, equation number 2, equation number 3. So we got three equations with three variables, and your variables are x, y, and z. Okay, so this this solution system, we can solve it through, remember the solutions? How they were called? Another one,
Oh, yeah.
igualación, sustitución, and there was another one, no? I don't remember the third one. Okay, but we got three
Wasn't
options.
there
Again? Who was talking? Okay, so, and then I remember, so, okay.
teacher? I think it was reducción. Well, I found it.
Yes, yes, you're correct. Reducción, definitely. Okay. Now, this is like the easy, well, not the easy, maybe the easier one to understand, but we can solve this also by matrix, okay? So when we solve this by matrix, and we can work it like with determinantes, and we also have the Gauss-Jordan solution, and we got a third one also. We use the matrix, and what we do is we take the coefficients, okay? So we take 2 minus 3 minus 5, okay? This is one matrix, and then 3 minus 4 and 1, and then we say we got minus 19 for the solutions, minus 2 and 6, okay? And 1, 1, 1. So this is what we call a matrix. Did you saw that on high school, or you didn't saw that?
Yes, teacher.
Do you remember? Okay, so you remember, but maybe you didn't use it anymore, so you just forgot. Okay, so what we're gonna be doing right now is doing that matrix solution. And what we do in engineering is we are gonna be including what we call slack variables. What's the word slack in Spanish? Holgura, variables de holgura, okay? So I'm gonna make some changes in my original form. I will be including slack variables, okay? And with those slack variables, then I'm gonna be able to work from the algebraic point of view, okay? Now, for example, I got my first equation here. Let me make some, descartar. Okay, let me erase this. Okay. For example, I got my first equation here, and then I say, okay, x1, it's less or equal to x4. So I'm gonna be including a slack variable. Which one? Well, it's gonna be an x1. I already got here, I already got x1, x2, okay? So my next slack variable, I'm gonna call it x3, okay? Like in order to continue with the numbers. So I'm gonna say, what I'm gonna be doing is right now, x1 here, I move it to my right, and then I'm gonna say x3 is gonna be equal to 4 minus x1, okay? Then I bring back my x1, and it's gonna be x1 plus x3 equal 4. And what I'm doing here, I'm eliminating the less equal, okay? And here, x3 must be greater or equal to 3. So watch, this x1 less or equal to x to 4 is gonna change to x1 plus x3 equal to 4. And for the computer, it's easier to manage equal equations than less or greater than, okay? So we're gonna be including slack variables, which is my other slack variable here. So I'm gonna be including here x4, okay? This is my other slack variable, and it's gonna be equal to 12. And I'm gonna be including in the next one, my third slack variable directly from this equation, from the original. I include a slack variable. Each equation will be including a new slack variable, x3, x4, x5, okay? And now I got what we call my augmented form of the model. Mi forma aumentada, okay? My augmented form. That means that I include slack variables. These slack variables are gonna help the computer to solve the problem from an algebraic point of view, okay? Because computer cannot go over geometric procedures, but they can go over algebraic procedures, okay? So, okay. Let's go over some ideas of setting up. So right now we're talking about setting up the simplex method, okay? We don't know, we just include in the solver in this information, okay, and this one, but the solver immediately changes to this, okay? That's what the solver does, okay? Includes the slack variables, okay? Now, my augmented solution, this one, my augmented solution is gonna be my decision variables plus my slack variables, okay? So when I talk here, we were talking about a point for x1, comma, x2. But when we talk about a point here, we got to talk about a point that it's for x1, comma, x2, comma, x3, comma, x4, comma, x5, because we included those slack variables, okay? So now this parenthesis will increase in 5 variables, okay? And that's why then we had before solution, but now we're going to talk about this kind of solution, 3, 2, 1, 8, 5. And the first one goes for x1, x2, x3, x4, and x5, okay? That means we're including the slack variables. So we're talking about the augmented solution, okay? Now, there is one rule. When the slack variable is equal to 0, when we got one slack variable equal to 0, it means that the solution lies on the constraint boundary, okay? Where exactly, if we have something like this, that means that we're in this boundary exactly when my slack variable is equal to 0, okay? When the slack variable is greater than 0, that means that we are in the feasible area, okay? And when the slack variable is less than 0, it means that is in the infeasible area, okay? And it's important to bring this because we're gonna be working with these slack variables, and you got to understand when it's greater, less, or equal, what's happening, okay? Questions here so far here? No? Okay,
No,
so
teacher.
remember, we're like preparing our original form into an augmented form, okay? Now, we got new terminology here. Let me go over the terminology. So our new terminology for this augmented form will be an augmented solution. What is an augmented solution? It's a solution for the original variables plus the augmented values, okay? We're gonna be talking a lot about basic solution, okay? So my basic solution is gonna be my CPF, remember? My corner point solution, the CPF, okay? But augmented, okay? That means augmented includes the slack variables, okay? In basic feasible solution, the BF solution, it refers to an augmented CPF solution, okay? That means that we are in a feasible solution, okay? We're gonna be using these terms, okay? So, when we we're working this equations, we say that we have 3 variables and 3 equations. So my degrees of freedom are 3 variables minus 3 equations equals 0. This is something that it's not explained here, but it's a concept we use in engineering, okay? This means that when it's 0, then we're able to solve the system because there are enough equations to get the 3 variables. If we had a conditions of 4 variables for 3 equations, okay, that means that we got our degrees of freedom will be 4 minus 3 equal 1. And that means we're not going to be able to solve this system because we're always going to have one variable that it's not solved, okay? And we're not going to be able to solve it, okay? What would be something like that? Let's say if we got 2x plus 3y, I'm copying the one we got on the over here, minus 5c, sorry, minus 5c, okay, plus 6m equal 19, minus 19, okay? If I add to each of this one an m variable, I'm gonna be able to solve for 3 variables, but the 4th one, I will never know exactly what is gonna be the value. That's what it means, the degrees of freedom, okay? Now, here in this example, we got 5 variables and 3 equations, okay? So my degrees of freedoms are gonna be my number of variables minus my number of equations, 5 minus 3 equal 2. And you're gonna ask, well, we're not gonna be able to solve this. Okay, yes, I know that. But see what it says here. It means that we have 2 degrees of freedom to solve the system, okay? Now, by choosing any 2 variables and setting them equal to any arbitrary value, let's say 0, then the other 3 remaining variables must be solved immediately, okay? So, yes, we got 5 variables here, 1, 2, 3, okay? But if I say that these ones are 0 or any arbitrary value, I'm going to be able to solve it, okay? Do you agree? Yes or no?
Yes, teacher, but so in order to do that, we're not going to identify the 2 other variables, right?
Well, watch what it happens. If simplex method uses 0 for these arbitrary variables, and we're going to call them non-basic variables, then we're going to be able to solve this situation. So we got 3 equations, okay? These 3 equations, but eventually what is going to be happening is that we're looking forward to make 2 of this 3 equal to 0. And when we have that, then we got a solution for our problem, okay? We're gonna be able to solve it, okay? And it's also by iterations, okay? So what we're saying here is it doesn't matter that we had included this slack variables because somehow through iterations, what's gonna happen is that my slack variables sooner or later are going to be valuing 0, okay? So if I got x1, x2, x3, x4, and x5, sooner or later, one of these 2, okay, or maybe x3 and x4 will become 0, okay? And then I might solve 3 equations with or 3 variables, sorry, 3 variables with 3 equations because 2 of them are already solved, okay? So that's how it's gonna be working. We have 5 variables, but through the iterations, because we're gonna be using the matrix work, the way we work a matrix, more or less like a Gauss-Jordan's solution. And I'm not gonna be going over that because it's not the matter of this class. But what we're gonna be doing is we're gonna make through iterations, eventually that 2 of the variables become 0 and immediately we're gonna get a solution, okay? That's how it is, and that's what we're gonna be doing next Thursday, okay? So I think this is, yes, this is the last point here. So basic solution properties, okay? So we got two types of variables. We got non-variables or non-basic variables, and we got basic variables, okay? Among the 5, we got x1, x2, x3, x4, and x5 for the example. 2 of them are gonna be non-basic variables, and the other ones are gonna be basic variables, okay? Now, how many basic variables we're gonna have? Well, the number of basic variables are gonna be the number of equations. Alejandra, do you remember how many equations do we have? Yes or no? More or less? No, okay. So we got,
4, teacher.
no, dear.
No?
We got
3.
1,
We got 3.
2.
I get lost with the last one. Yes,
Don't
I
worry,
can-
that you get lost with the non-negativity, okay? Remember, we don't use the non-negativity equations. So we got 3 equations, so we got 3 basic variables, okay? That means that from these 5 variables, 3 are gonna be basic variables and 2 are gonna be non-basic variables, okay? That's how we're gonna be working always, okay? Now, at the beginning, non-basic variables are set equal to 0, okay? And we're gonna give an example right now, okay? So basic variables are equal to 0. That's another basic solution property, okay? Now, basic variables, sorry.
Yeah, teacher, you're missing the N. Yes.
Okay, non-basic, okay. Basic variables then are gonna be obtained by solving the system of equations, okay? So we say, if we make, what I said just before a few minutes ago, we got 5 variables, okay? And if we say that these 2 are my non-basic variables, that means they're equal to 0, then I can solve the rest of the system of equations because we got 3 equations with 3 variables, okay? Immediately, we're gonna be able to obtain the values of the basic variables, okay? And then we say, if the basic, this is a criteria we're gonna be using. If the basic variables satisfy the non-negativity constraints, then we got a BF solution, okay? So if the solution of x3, x4, and x5 satisfy the non-negativity, when we say x1 all the way through x5 are greater or equal to 0, if this happens, then we got an optimal solution. Otherwise, we will have to change one of the non-basic variables to with a basic variable. And then we're going to start moving and doing iterations, okay? So let me illustrate this with an example, okay? This is a little bit like, I got the feeling that you must be right now in the position that, yes, I understand, but where we're going, right? Okay, I'm I'm putting the basis that will let you understand what we're going to be doing on Thursday, okay? So just don't get desperate, okay? Now, in order to illustrate this, let's say this is my 5 variables. Which ones are my non-basic variables, Dani Rueda? If this one stands for x1, this is x2, 4, x3, x4, and x5. Which ones are my non-variable, my non-basic? Yes, these are my non-basic variables because they are equal to 0, okay? So if this x1 equal to 0, x1 equal to 0, x2 it's equal to 0, and x2 it's equal to 0, then we can say that x3 is equal to 4, x4 is going to be equal to 6, and x5 is going to be equal to 18. That's where these numbers come from, okay? By substituting or by just putting the zeros to x1 and x2. Okay, now, because all of these 3 basic variables are non-negative, we can say that this basic solution is a BF solution. Okay, now be careful, it's a BF solution. Now the question is, it is the optimal solution? Is this an optimal solution? Well, I don't think so, okay? And we're gonna see that on Thursday, because in order to move from the current BF solution to an adjacent one, what we're gonna be doing is we're gonna be switching one non-basic variable with a basic variable. And then we solve the system of equations. Okay, how do we do that? That's gonna be easy. Now, instead of having x1 and x2 equals 0, let's say for some mathematical decision, now we say that x1 it's equal 0 and x3 is going to be equal 0, okay? And when that happens, how this is going to move? What are going to be my new values for x3, x4, x5? So we say that x3 is now 0, so x1, this x1 is 0, x3 is 0. Okay, so we got x2
4, right?
and x4 equals 6, okay? This one, it's equals 0, so we got 2x2. So we got, watch, we got 2 equations with 2 variables, okay? And that one, yes, we can solve it somehow. Yes or no?
Yes.
Let me write this x2, x4, x5. What time is it?
5:15.
Okay, we got a few more minutes. So let's go over this. Let me add a blank part here. Okay. And this is what we're going to be doing on Thursday. Okay. So oops. So this is what we got. Okay. So our new solution, our new system of equations is 2x2 plus x4 equals 6. And then we say that the other one was 2x2 plus x5 equal what? 18, okay? So the computer, what we'll be doing is, this is gonna be all negative. Well, let me make this one negative, the first one negative, like this. This is what you call the reduction system. So these ones are erased, we add them, and then we're gonna have minus x4 plus x5 equal 18 minus 6, it's 12, okay? And then we shall, I just get lost here because I got two equations. I wanted to go farther, now I'm between two situations. Okay, and then what it's gonna, okay, let me go back over here. It's x3, x1 equal 3. No, I'm trapped here. I need to look for a solution on this. But let me work it for next class and give you a solution. We're gonna stay here, okay? But what we're gonna be doing is we're gonna be switching this we're gonna be switching here, for example, this one stayed the same. And here what we did is we switch the basic variable, okay? The non-basic variable, this non-basic variable was switched for x3, okay? And now x2 is not 0, only x1 and x3. And then we'll come to a solution from a matrix point of view, okay? Let me prepare it for next class, okay? So,
Yes, teacher.
let's go over this before we continue. So we saw we have to work on the algebraic procedure, okay? So how do we do this algebraic procedure? Introducing slack variables. And when we introduce slack variables, we get an augmented form of the model, okay? Now, the slack variables, there were three conditions. Remember that we're gonna be using. If the slack variable is equal 0, it means that we're in a constraint boundary. We're standing on a constraint boundary. If the slack variable is greater than 0, that means we're in the feasible area. And if the slack variable is less than 0, it means that we were in the infeasible area, okay? And in order to finish the last part, let me move this, okay? We say that our algebraic terminology was augmented solution. It was when we add the decision variables plus the slack variables. Now, instead of saying CPF solutions, we're gonna call it the basic feasible solution, okay? Where a basic solution means that we're in a corner point solution of an augmented solution, okay? And our basic feasible solution, it's like talking about our CPF solution, but with slack variables, okay? So if we don't have anything else, we see you next Thursday. Have a nice September 16 holiday.
Thank you, teacher. You
You
too.
too,
Thank you, teacher.
Thank you, teacher.
Have a nice day. Enjoy.
Okay.
Bye.
I'll be loading this information tonight, okay?
Okay.
Okay.
Thank you, teacher.
Thank you.
Bye.
Bye.
Teacher, I had a little problem with my solver on the homework task.
You in your homework?
Yeah, but I told you I put a little note on Blackboard. It's just that when I do the solver,
on Brightspace, no?
Brightspace, yeah.
Okay, because for some reason I'm not able to open Brightspace. I got to get in touch with the technology information department, but okay, I'll go over it. Don't worry.
It's just that when we were doing the other class, when I
Yes.
showed you my screen, my solver wasn't like complete because everyone gets like the numbers like from this task is what it was like 7 and something, and I don't get that.
Okay, I might know why. Do me a favor. Start from a blank spreadsheet.
I did actually.
And you have problems with that?
Yeah.
Okay, because we had that problem with the other class, and for some reason, what it was happening, remember that we made a copy, like a copy paste from one spreadsheet to the other one, and then we start changing here the numbers. And for some reason, we weren't getting the numbers correct. But what was happening is that one of the formula, it was like suma producto, these numbers multiplied by the units, but it was taking the units from another.
But maybe when you open my homework or something, you can.
I'll go over it and see what's going on, and I'll let you know if that's the problem.
I did everything like I was supposed to, but I don't really.
Don't worry. If that's a problem, I'll let you do it again.
Okay. Thank
Okay.
you. See you later.
Have a nice day. Bye.